Welcome to the afternoon. Hope you all had a nice lunch. Gives me a great pleasure to introduce our next speaker. Actually someone I know pretty well, and he lives on the Gold Coast, and he's often talking at LCA and travelling other places. So he gets, in 2020, to be in his home city for a change, which is pretty awesome. So Ben is going to be talking today on ROS on your robot. This is a pretty long-term project he's been working on for quite a while. And today is the tale of an inside and outside robot and two arms. Please welcome BenMartin.
Alrighty, I was sort of in two minds as to whether to do demos of robots first or at the end, or so I think yes, up front for some. I started off building Terry, which was an indoor robot and had a couple of high torque motors and was just remote control with either a remote that I made or a PlayStation 3 remote control. And as it went along, I read about ROS and how you can do mapping and navigation, and I thought that sounds like a good thing to do. So then added wheel encoders and basically built this monster that you see before you. I was going to do a live demo, but about 1 out of 20 times it doesn't go to exactly where you say to go, so I thought that one time is going to be when I'm standing here and it starts careering off and running into people. After I built that, I started building this outdoor robot, which I have slides of close-ups of parts of the robot. And I'd heard about a challenge where you're supposed to make a sample retrieval type robot, which is fully autonomous, that NASA put out. And I thought that sounds, that sounds difficult enough. So I started building this and initially made it with a Raspberry Pi. And then when I started putting more computing power onto there, discovered that the suspension no longer worked. So the suspension on here is for mountain bike suspensions that I got from China for about $50, because you have to be reasonably sort of thoughtful when you're bankrolling the entire build yourself. I found one tip that I found when I was making these was if you have external keyboards, you can have basically
My name is Terry.
specific buttons. No evil robot laughs. So instead of logging in with these, if you use input exec, you can run commands from any key on the remote keyboard, which solves the chicken and egg problem where if you have a input device and you're using ROS to give commands to the robot, you need to actually have the entire ROS stack running in order for that input command to be received. Whereas in this case, input exec comes up as the robot comes up. So you can then use the keyboard to start ROS or change how the robot's feeling at the time. I'm not sure how the Houndbot is going to run on stage because I run it on grass. So this could be interesting. This could be a very short talk as well if it goes the wrong way. So here we go backwards. Yay! Not too far backwards. Not too far backwards. Yeah. So forwards and left. Can we do left? No, I'm actually a little bit squeamish about running that into those screens without first seeing whether or not I can turn. There we go, I'm turning a bit now, a little bit. So I might just leave him over there, I think. So on the back of Terry, I've got a Lynx motion arm, which I've talked about before. And initially I was trying to use the ROS Movelt stack to control that, which has a really nice interface and a planner, and you can choose how it's going to move the arm and all of this sort of thing, and found out that you couldn't do it because there weren't enough degrees of freedom in that arm. So then I went and bought a alleged 6 degree of freedom arm from China, which is this guy, and found out that they were counting the motor that grips things as being one of the 6 degrees of freedom. So you fairly quickly find out that that doesn't work. I have some screenshots of the control for this, but if I turn that on and power it up, you can tell the interface to plan, execute. There we go. Because the Movelt stack knows where each joint in the robot arm can be and how much rotation each joint in there can have, how long all of the parts are, you can tell it where you want to have the end effector. And in the interface you can say just select a random valid location, which I will choose something that's going to not be too bad. Okay. And of course, being demo time, the stop button and the execute button don't seem to want to work. Of course, finding it when it's on power is also not a good move. Yes, just lay down. So I've got slides for how to actually set up Movelt, and the main thing that takes time there, you need to have 6 motors in your arm. If you don't have 6 motors, then it's just not going to work. Like I tried to get it working with the 5 before I extended it with the extra servo. And the main difficult part is really setting up the description file, saying how long parts of the arm are, where all the motors are, how much they can rotate, where their center is when they're going to rotate. And it's sort of, having played around with Movelt, trying to get it to go, it took about 2 days to get the arm to function reasonably well like that. So Terry has grown from using a PlayStation 3 controller, which I forgot to do that. Actually, bringing up the robot is always handy. A PlayStation 3 controller to move it around, which once the controller binds, I may move it around. It's a lot more nimble. The outdoor robot, I was sort of a bit concerned on this surface going too fast, and you need to have speed in order to turn left and right. Okay, we allegedly have success. We have flashing lights. There we go. I was going to say, the whole doing a demo thing just sounded like a great idea at the time. I found on here, the top screen was interesting 17-segment display, but then I found if you can only display 6 characters, even though they're really large, you can't get much information across. Whereas if you have a dot matrix LED display, you can have a blinking light, which basically shows that the ROS stack is still functioning, because if it's not functioning, that light doesn't blink anymore. And if you're moving with the joystick, handy for other people, you can have how much power you're putting in, whether you are moving, whether you're turning in a certain direction. So direct feedback for anyone. And if you are doing a pan tilt operation, because in this case, if you're rotating the screen around, because it rotates very slowly, and it helps if I give it power. Yes, because it rotates, as you may be able to see, rotating very, very slowly. Having a visual feedback for people who are not that close to the robot and the pan tilt. In theory. But I hope we've actually turned everything on at the start. So panning backwards and then panning back forward again. And of course, controlling the arm and moving it up and down and left and right, which maybe not the best angle to be able to see that happen. That's going to keep doing that. So the main thing I found was once you can move this around, moving it around with a remote control is the simple part, but then trying to get it to actually build a map of the house when you're moving it around using one of the connects to get a depth image and convert the depth image into a laser scan of where the walls are, remember where the walls are, and based on the power that you're giving to the motors and the feedback coming back, remember where you are relative to other things, and then turn around and navigate with that. You appreciate the difficulty going from direct drive, where you've just got a remote control, to something that's trying to map and trying to actually go into the kitchen without you being there telling it exactly go left, go right. So there we go. So getting into robotics now, more regular, less direct demo-y side. It's fun and games for people who have a software background. So getting into electronics, into robotics, I didn't know anything about electronics, and some would argue I still don't, but there's a lot of varied things that you can look at: the electronics, building motors, how you're running batteries, the issues with LiPo batteries and the charging thereof, playing around with aluminium and maybe getting trapped into building and playing around with CNC stuff to make parts for your robots. The PlayStation 4 controller is held on by a custom-made mount. The screen that I added on this side is in a custom aluminium mount. I would recommend, actually, if you are doing a ROS robot, adding something like the screen at 45 degrees so you can follow the robot around and watch its thought of the map and its thought of its orientation in the world. So then you can see directly, because if you're starting out mapping, if your odometry is wrong, as you move toward the wall will actually disappear in front of the robot and get further away. Because your odometry is not feeding back correctly, the reality of how far the wall is from the robot is what reported correctly by the Connect. But ROS will actually think that your robot is still closer to the wall, so therefore the wall has moved. So being able to see whether or not the things that the robot is seeing in front of it are actually valid at that depth. So yes, as I say, if you're starting out doing a direct drive robot with a remote control, you can sort of whack it together with a bunch of off-the-shelf electronics. And that's relatively straightforward, but if you're trying to then do a map in any way, or like with the TensorFlow things, trying to get it to do things where you're not at the control, that's where it becomes quite interesting. There's varying power sources. Terry's got an external laptop battery, which is made by a very reputable brand and actually has the aluminium shell, which you can see behind the AA battery pack up there. Or you use AA batteries, or you put you fold and you start putting LiPo batteries on there. If you're doing LiPo batteries, a bucket of sand is always good, and also a bag to charge them in, because if you dig up a few YouTube videos for fun and games, you can see what happens when you throw water on those things and how badly they go off. So what is ROS? Has anyone, how many people have used ROS? Okay, so I didn't really know what the spread in the room would be. So you have a federation over a network. You have publish and subscribe. To me, the main value in ROS are what ROS nodes are available. So if you're doing navigation, there are nodes for maintaining a map, nodes for creating a map, for doing localization in your map so that you can look at what the radar's seeing, where the robot thinks it roughly is, and it can sort of move itself in its mind by 10 centimeters based on what it's seeing. There's things for lifecycle management, so if things fall over and you've got microcontrollers and the code to do that has crashed, it'll restart that code if you like. RViz and Gazebo and Web, and basically a framework sort of from, well, the head to toe part being that you can have anything that Arduino can be programmed with. You can have a ROS publish subscribe right down on the microcontroller level and send typed messages, and they'll bounce through your main robot and actually straight through to a web interface with JavaScript, so you don't have to play around with multiple different firmwares. I have a few examples of what ROS messaging is like. So you have topics to send messages to, and you can echo a string to topics. I'm just trying to work out my speed here. Might just skip over that one. There's, depending on which language you like with ROS, there's C++ or Python. And I knew this remote control was going to just keep doing that every now and then. Let's bring that over here. So in this case, I'm sending a string to a specific topic name. And you can remap topics, which is very handy, because if you're publishing, say, to that robot arm, and you're saying, I'd like all of your joints to be at these specific positions, and then the microcontroller is going to PWM to control the servos to do that. If you have that going to a specific ROS topic, you can rename that topic and call it, topic old, and have another node that subscribes to the topic old and actually outputs to what the microcontroller is expecting. So if you want to inject sinusoidal encoding, you can do that without changing all of the code that commands the ARM. The life cycle management, you can have a node for controlling the ears on the Houndbot and tell it basically where it is and tell it to launch it, relaunch it. And if you've got the microcontroller side, there's an API to do publish, subscribe, so you can talk to the rest of the robot. You can send out your sensor data, or in the case of the robot arm, you can take the data and turn it into servo stuff. I found that the ROS stuff for micros is a little bit SRAM heavy, so if you're using things like the Atmel 328, you may run out of RAM very quickly with 1 or 2 subscribers. So you want to be sort of mindful of that and maybe choose other micros or just do 1 or 2 things on one 328. That's handled by a Python node on the computer running ROS, which if you've got multiple of them, I'd recommend using something like UDIV. And if you can get a micro that has a serial that shows up in UDIV, because Terry's got 6 or 7 microcontrollers, and if I didn't have UDIV naming them properly, every time I changed something in any of the hubs, they'd move around. So either find something that has a serial that it's advertising, or find 6 different microcontrollers you like, so that you can pick them off by the type of microcontroller instead of their ID. The Arduino API is very similar to the C++ API. I sort of have a few of the lower level details. So if you have a subscriber, basically you tell it a function to call when a message comes in. In this case, it's just printing the number to a character display. So if you're actually on the computer side for something that you're running on the microcontroller, this is what you would do on that side. And this is useful in many ways that don't seem immediately obvious when you start using it, in that if you're using the Python serial, not only do you have to not talk directly to the micro over a serial interface, but that will interrogate the other end and ask it what it will subscribe to and what it will publish to. So if you have something on here, you can unbolt that system, that microcontroller, take it to your laptop, plug that in and run the Python serial, and it will interrogate the other end and say, oh, okay, you were expecting to see 3 messages of these types. And then you can debug it on the other computer without having to move any of your tooling around. And the other part being that if you set up your make files properly, you don't have to use the Arduino IDE. So you can basically upload directly from the robot to a microcontroller that's on the robot without having to think, how do I get Arduino on here? How do I unplug this, replug it? As I mentioned earlier, you can get through to JavaScript stuff from ROS messages. So you can fairly easily make a bootstrap type interface to control your robot. And in this case, controlling the X, Y, Z and the claw position from a handy web interface. Again, the web interface, like a main ROS node, subscribe to the battery voltage and display the voltage from the main robot, or display that in the web browser. So basically, in this case, you're getting the voltage from a microcontroller on there, through the motherboard, through the web interface, over JavaScript, and displaying it in the web browser. So the ability to get information from one end of the robot, be it in the micro or on the actual machine, and put it on a web interface or interact with it through another device, I think is a huge advantage to using ROS if you're building a robot. In this case, when I'm using the XYZ, I'm just using an array of float 32 numbers. So you can create your own custom message types if you want to have X, Y, and Z. But if you're just using an array of float 32, then anything else that wants to talk for floating point numbers can talk to the ARM. It may not make great sense if it's just talking large numbers and the ARM says, great, you want me to move to 32 million, I'll see what happens. But you have the option of doing it. That's, I suppose, the joy of no type checking. The components for building a robot such as Terry, you've got the manipulation of the ARM, the sensors. The main thing when you're looking at doing navigation on this is the robot base, where it accepts a speed and a heading, basically, and it's supposed to try to reach that sort of goal. So hit this velocity, turn left 10 degrees. And the feedback coming back to the navigation stack comes from your wheel encoders, and it basically says this wheel's turned 1,000 clicks, this wheel's turned 32 clicks in the last this amount of time. So in that case, on Terry, because it's way down on the stage, the encoders are the black box which is attached to the brass gear on the alloy gear, and that gives an 8-to-1. If you're not too familiar with using the quadrature encoders, that encoder will give about 1,000 pulses every time it rotates around once. So if you have that on an 8-to-1 on the actual wheel, then you're getting 8,000 pulses every time the wheel is rotated one rotation. If you're doing this, there are, yes, Hall effect encoders which do the same thing, but they use a rotating magnetic field, and you can get a lot better precision, and you also get no kickback, which you'd get with the gearing. So you need, on Terry, you need to smooth over the fact that the gears will jolt as it's going over carpet or over one of these bumps. And that's what the AMS chip looks like if you're going to do that. The hard part there is sourcing the magnets, because you need magnets with certain polarity and attaching them to the shaft so you get the right rotating magnetic field. And you'll also need to either find a friend who has an oven that they don't want to use anymore, or go and buy one so that you can solder SMT components at home. So you find there's a lot of little avenues that seem like they're a small avenue, and then you start wondering, why am I building a CNC? I was supposed to be doing this. If you are doing robots, getting into building something like Terry with a Raspberry Pi, then you're going to need a motor controller or a dual H-bridge, which is basically what's on the screen there. So the thicker wires are for the power put down. Some of the gear motors, you'll find if the motor is getting overloaded and stalls, the motor will want to chew about 20 amps. And if you don't have thick enough wires, it's not a good thing. Actually, leaving them stalled at 20 amps, the motor will basically heat up and your life for the motor will go down. So I'd avoid that, but also I'd avoid having the wires catching on fire before that happened. The suspension on the Houndbot, the wheels, which is conveniently located behind me, the wheels came off a small child's ATV. So a lot of things in the robots that I've built have been foraged. In this case, I got 3 wheels for free and sort of bought the 4th wheel to match. Custom suspension, you start playing around with. If you get outdoor robots, it's lots of fun because you start drilling and cutting aluminium parts and putting suspension and getting into mechanical engineering side of things. The suspension off these are off a mountain bike suspension, so $50 for the 4 coils. And the suspension's way too stiff. I think it's about 600 pounds per inch. So you get the rocking like in the old leaf spring sort of things from the 1920s before they got car suspension working properly. But it's better to have the suspension too stiff. Initially the suspension was far too soft and it looked okay, the robot would sit okay, and then you drove it and the wheels would just come straight out and the whole thing would belly out. So that's, at least it drives with hard suspension. The wheels on the Houndbot have been mounted with, I've basically cut the 2 hubs apart and CNC'd my own wheel mounts. So you can see how far the whole custom building of robots and CNCs goes. I've got 2 connects on Terry. The top connect is so that the pan tilt, it can move the connect around. And with ROS, you get a placement so that you can say in your description of the robot in ROS, you say this bottom connect is 30 centimeters off the ground. It's at this location relative to the core of my robot, and it faces forwards. So you could then say, you could describe this arm completely, and then say, there are these motors that can turn, the actuator, this is where it would be, and then the robot has some idea of where it is in the world, and it moves around, but then it's not a perfect idea of where it is. So if you have another connect, you can turn that around, and if you're trying to pick something up that's that large, you can see that it's here and the robot actually thinks it's physically a little bit further over, and do closer localization when you're trying to pick things up. Yeah. Initially, when I was making this, I had bought a very cheap slip ring, which is below in the pan tilt, just sitting in here, so that you can run some 12 wires through it. And I initially thought, that's great, I'll cut the Connect USB 2 cable and wire them up and run the Connect in the head unit. But the signal strength the signal quality through that slip ring is nowhere near what it needs to be to run USB 2. So now I have at the top an Intel Edison, which connects to the Wi-Fi access point over there and streams these cameras over the Wi-Fi to the computer in the base. You can get USB slip rings that will do USB 2 or USB 3, but you usually pay quite a bit for them. So building hobby robots is partially also about triaging what's going to cost things and what's going to be sort of acceptable to bolt on. The pan tilt unit's probably the nastiest human interaction element on Terry, because the brass gears have got a 6:1 ratio internal geared. So if you get your finger in there by mistake, you're probably not going to get it out in the same sort of quality that it was when it entered. And you can't really fight it either. It's got so much torque that you just, you'd be yanking at your finger and the gear would say, okay, have part of your finger back. But for Terry, most of the navigation is done with a Xbox like the Connect 360, which now, if you're building a robot with ROS yourself, you can buy one of those at various retailers for about $10. They're a very easy thing to hook up. You may need to cut one of the cables and inject 12 volts DC. I think they want to lap up about an amp at 12 volts, so you need to cater for that with your battery. On the other hand, if you're connecting a PS4i to do stereo vision, you're going to need to cut and resolder a USB 3 cable, which on the third attempt I got it to work. It worked okay on the first attempt, and then I plugged it in and it said, yes, you have that camera there. And I said, great, give me an image. And it said, no, I'll go to high-speed USB 3. And then it said, now my USB bus is dead. So you can do those. The reason that you want to do stereo imaging on a houndbot or an outside robot is that the Connect relies on infrared, and the sun basically kills infrared, so you can't use Connects outside because you don't get the same signal pattern back. Again, looking at this and talking to somebody who is looking to build an outdoor robot or a robot with stereo vision like the Jetson Nano, and you can pay somewhere $200 or $300 and buy a stereo camera, which comes with CUDA stuff, so you get a depth map done on the GPU. So if you're willing to sort of buy that rather than hack an old PS4i, then you would be ahead of having to write your own GPU code just to do the depth map. The robot arm's controlled by a servo controller, which is also repurposed to control the pan tilt. So again, it's all sort of geared. I have probably skipped over that part, but a torque multiplier there and now a counterweight at the base. So if, yeah, that's going to be on. If the motor's not on, then you can push it back 10 degrees and the counterweight holds the head in place, whereas without a counterweight it just runs away. Manipulating things on Terry is done with this. I think it's a 4-degree of freedom arm. So then I've just basically directly written the trigonometry to do that, to go to an XYZ position. So on the front, I have a lot of, the biggest feedback to the humans thing that I've seen is the audio, being able to go over and say, does the keyboard actually work that is controlling various specific navigation things, and just sort of hit a ping command.
My name is Terry.
But also if it's moving around, and ROS will detect if it's going over here on a navigation and I stand in front of it, it'll say, okay, you're blocking my way, can I route around you? And if it can't route around you, then it'll stop. And obviously, if it stops and then you move away, it says, great, the obstacle's gone and I'll go. But if you have speakers on board, if you stand in front of it, it can say, I'm waiting for you. Or, I've detected a transient object, I'm waiting for that to move. Otherwise, you have to go to your laptop and open it up and look at RViz and say, what's happened? Why aren't you doing what you're meant to do? Is it broken again? So on Terry, I'm using a PS3 remote and a keyboard, and I initially started using the PS3 controller on the outdoor robot, and then I got this and mounted the aerials properly. The PS3 controller, if you got sort of too far away, like 10 or 15 meters away, the controller would intermittently drop out, which is not so great when you've got a 20-kilogram robot sort of careering along. Especially if you don't have any sort of dead man logic and there's no, oh, you were wanting 100% straightforward and now you've given me no more signals, so 100% straightforward it is. And then you see the lady with the pram, or the dog, or the car, or, you know, various bad scenarios, various bad days ahead of you when that happens. So I highly recommend investing in something like this if you're outdoors. That was a fun story too. The controller for that, which, you know, the picture probably shows it better than me highlighting where it is on the robot, receives the signal from this, and you can get an iBus, like a almost UART type protocol. And I had that initially hooked up to a Arduino Nano, and about once every 5 minutes it would randomly stop giving UART data. The exact same sketch on a Uno, for whatever reason, works fine. So, you know, I say this and the robot's still there, it's not deciding it's going to get false commands. So be prepared in these cases for miscellaneous debugging. In this case, both of those Arduinos were cloned Arduinos from China, so it could just be that one batch was strange, or who knows. The main components when you're getting into building a navigating robot, as I briefly mentioned, were the mobile base, where you have a go this velocity, go this direction, and it has to project or publish odometry information as to what each wheel has done. And you can have a robot, in that case, where you're doing differential drive, so you turn by turning one wheel slower than the other wheel, and the robot skids around the corner. By default, I think ROS wants you to have an omni wheel, so you can go sideways as well. But you can turn that part off. So you run in two modes, and in one mode you go around with GMapper running and you build a map of the world where it thinks all of the walls are and all of the fixed static objects, like where are all the chairs, where are the objects that I need to avoid. And then you can run in AMCL, or basically navigation mode, so you can say you have this map, go into the kitchen and face the fridge. And then you just sort of wait and see. The robot most of the time will do that, and sometimes it will just turn around where it is and head the other way and say, I found a new path to get to the fridge. You don't know about it, but here it is. So, yeah, the PID for the fly-by-wire on this controller, if you're going forwards and backwards, because this is actually a flight controller, so it will hold your position for velocity. So that's very handy, because in this case I can direct PWM the motors, and so if it's 70%, it'll sit at 70%, and if I gradually move it back, then the motors don't get too annoyed with me. On Terry, I've done a fly-by-wire, so if you say on the remote control go forwards, it'll say great, now I will gradually ramp up to going at the speed you want me to go. And if you let go of it, it won't just sort of immediately lock in place and the whole robot tops over because it was going at a reasonable pace and then you've said just stop instantly. So if you're flying by wire that way, it's a huge plus, and the navigation stack is quite happy to have your mobile base have PID control, and it won't sort of it won't conflict. That's the three modes that I was just mentioning. So when you're building a map, this is what RViz looks like. This is probably one of the huge, well, it is one of the huge advantages to using ROS. In RViz, you can turn on a number of plugins that know how to handle data of certain kinds. And in this case, I've turned on show me the robot model, show me your laser scanning, which in this case has come from a Connect, and show me your idea of what you think this room looks like. Give me your current map that you've built from me driving around. So you can see the position of where the robot is, where if you, and may or may not be, yes, the white dots are seeable. So the white dots on that map that are in front of the red, sort of to its right, what the Connect's laser scan is currently giving. So that's where it thinks the edge of the, the obstacles that it may run into are. And you can, it's OpenGL, so you can rotate that map around and see, they are actually above the black wall parts. And this is what I was saying, that would be handy if you were going to, it would speed up your time, I think, if you were going to do this sort of thing, having a screen on the robot at 45 degrees like there, because you can drive around and you can actually see this running. If you're running this, the Terry CPU-wise is a J1900, so quad-core Atom. It initially had 4 gigs of RAM. If you run RViz on there, you lose about 1 gig of RAM and about 120% of one of those cores. So if you can run that on a laptop, and you can obviously connect to it from the laptop and use ROS on multiple machines at once. But if you're going to have it on screen and you're going to have it on the robot, you need to sort of prepare CPU and memory for that. When you switch over to navigation mode, initially I've sort of said, okay, run the navigation stack. And all of these little red arrows are basically the point cloud of where I've said to the navigation stack, your robot is here, you're facing this direction, you are at this point in the world. And because I've done that, it started out saying, okay, you've said I'm exactly here, I'm sort of uncertain, so I'll say I'm like within half a metre of where you've said. And as the robot moves around, it starts to get feedback from the Connect saying, oh, there's a wall along here and there's a wall along here on my map. So my point cloud shrinks in and becomes like very close to the foot of the robot as it moves around. And every now and then the robot moves on the map because it needs to say, the odometry that I've got from the wheels is incorrect. You said that you've moved a metre and your wheels actually slipped a little bit on carpet at some point and you've only moved 95 centimetres. I can tell that because on the map I can see this, and from the laser scan from the Connect I can see the same thing, but it's 5 centimetres away. So the localisation then adjusts where the robot thinks it is based on the objects that it's seeing as you are driving around. And I tried doing dead reckoning, which is basically driving around with no feedback from the laser and no adjustment. And you will find in a modest sized room, if you're using gears on your odometry, you'll probably be out by 15, 20 centimetres just by doing a lap of the room. So you need to have something to handle that variation, I suppose. So if this is the robot arm that I was showing earlier swinging around madly. Initially it came without the piece sort of toward the base there with the holes in it, and that's an Activotics piece. So if you're looking to build small custom robots, I'd sort of recommend at least looking at Activotics, which is channel and various other things and mount points that you can just buy. So it's sort of like Meccano for adults or something, or more expensive Meccano. So in this case, instead of manufacturing my own part, I just used a piece of channel there and sort of got the servo in to get the six part of the thing. And the electronics to control the arms, just basically a PWM controller and a Uno knockoff. As I mentioned at the time, sort of in passing, this is what the specification of that arm looks like, which is URDF, which is not anything to do with RDF or the semantic web, sort of name clash. So you're controlling joints and you're controlling links, and you're saying that you're building up a model for Movelt to see. Movelt is generally used by things like automotive arms. So if you have an arm that's worth $200,000 and is putting a bolt in here, Movelt will quite happily do that for you. So if looking at it in that light, you can sort of see why they're expecting you to have 6 motors on your robot arm, because you're not going to buy a $200,000 arm without 6 degrees of freedom. The flip side there is that with 6 degrees of freedom, there's hundreds of ways that you can reach various points. So with the arm with 4 degrees on Terry, there's only really one way you can configure the arm to have the actuator at a certain location, if indeed it can get there. But with 6 degrees of freedom, you can sort of hold the actuator in one point and swivel the arm around. And you have that ability to have hundreds of solutions. So using Movelt with its collection of motion planners becomes more interesting rather than trying, unless you're right into moving robot arms, in which case I'd probably contribute a new library for that. But this is what the origin and the length, basically how to set up where a joint is located, what angle it's going at, and then you'd have a link of 25 centimetres to the next joint, and then you'd say this joint can rotate, and this is its dimensions that it's able to rotate in, which, yes, it gets smaller and smaller and smaller. So once you have a reasonable description, the Movelt wizard, I had some bad feedback about using Movelt when I complained to various people at groups, and I said, hey, how do you do that? And they said, well, that's great. You just fire up an editor and write your own matrices and do this and that. And I thought, bad advice. Use the wizard. And you get in this case, the arms positioned straight up. but you do get an immediate sort of interactable arm saying this is what the model that you've given me looks like. Does that match reality at all? And it can work out joints that can never collide, so they don't get actually considered in the movement. You can set up custom poses, so you can say instead of being straight up, like I'd like my home pose to be sort of arm out or claw on the table, so that when the power is shut, the whole arm doesn't go bang. And then when you get to, this was the interface that I was seeing on the black laptop over there when I was moving the arm. So you can either move the end effector, and so I'd like to have the end effector at this location, at this angle, make a plan from where it currently is and swing over to there. Or because you've described all of the joints and the lengths of all of the parts of the arm, you can just click in the middle part, there's a select goal and it says random valid. So if you hit update, it just keeps randomly generating a valid end effector position. And then it's great for demos because you don't have to sort of play around trying to get a selection of an end effector to somewhere that doesn't really matter. And that was where I was meant to have my demo of the arm, but I've already done the demo of the arm. So the oh no part and the various other parts aren't there. So I guess it's potential question time. Yep.
Whereabouts do you get your end effectors from, and do you design your own?
Yep. Where do I get the end effectors and do I design my own? So just the very tip or the whole arm?
No, just the end effector.
Oh, okay. That just came with the Lynx motion arm. So it's just a servo in the end that just drives the slow pincering. And likewise for this guy, that also came from one of the various internet retailers. So this arm, I thought it was reasonable value. I think the arm, the aluminium part of the arm was less than $100. And then you could match it with, I think I've used 7.4 volt metal servos. So that whole arm you can put together for less than $200. But they also sell like a tendon-driven hand that you can put on the end. Yep.
How important is the odometry? Can you get by with just the Connect?
I haven't tried that. I think I would say from what my experience is of moving around inside the odometry is fairly important. Certainly to using the navigation stack out of the box. Because if your odometry is wrong, the two signs that you know that that's the case are the wall moving and as you move forward. Well, the other one is if you're spinning around. If you come back to, like if it's here, it should see the arc of this table, and in RViz you'll be able to see the curved dots. But if your odometry on your differential steering is off, your curved dots will be off when it's pirouetted around 360. I will be finding that out because this guy, I could possibly put Hall effect encoders on the Houndbot, but because it's running on grass and on gravel, whether or not you think the wheels turned and it's just nothing.
So with the robot grippers, have you run into issues with overcurrent on the sort of when you try and grab something and suddenly it's gone too far and it's sitting there trying to reach a point and then it can't get any further, so it just overcurrents the servo?
No, I don't really monitor for current runaway, so if it grabs something and the thing doesn't want to be grabbed, then it's sort of, it's up to you to stop it, I guess.
Is there sort of mitigating strategies for that?
I don't know whether to move it actually. I mean, because some of the higher end arms would have pressure feedback. So I'd say that there's something in Movelt to automatically do that, but I'm not familiar with it, but I guess that's the other thing. There's always that triage of how much money you throw at something, and if pressure sensors are going to be another $50 on top of ARM, then you sort of say, don't get caught. That's
Chris would like to know if you've used ROS2 and what your opinion is of it.
I like that ROS2 runs on things other than Linux, which is probably something that I should hide for saying at a Linux conference. But people have Windows laptops and people have Mac laptops, and being able to run RViz on a laptop that's not running Linux is quite handy. From my understanding of it, the transport layer that they're using underneath has gotten a lot better, so the publish subscribe is a lot more efficient in ROS2. But also I've heard that not every node in ROS 1 has been ported to ROS 2. So I guess it depends on the robot, but if I was going to update Terry to a new ROS 1, I'd probably look at whether I can use ROS 2 instead and move to ROS 2. So that's...
Just actually a couple of questions. I'm cheating here because I caught up with you in the car park. You've got 2 connects on there. Is that simply to add to the effectiveness to make it actually more effective, or is it for, or are they used for separate purposes?
The use case I had was for this one to turn around. So if you're interacting, like to actually help with the interaction with the end effector. You know, it's sort of handy too to be able to sort of turn sideways so it can look at you as it goes past and so, haha, or if, you know, just raided the fridge.
Just the last thing I wanted to know is, how many different processing units have you got on something like Terry?
How many processors?
So, no, processing units. So like you've got, I don't know, whether you're using an API, you mentioned you're using Arduinos and various other components. You're obviously, they're communicating via various things. How many of those different units would you have on something like Terry? Do you have one controlling the arm and one controlling the driving and one controlling, is this how you've constructed it? And is that the normal way that you would construct something like that?
I do, if I was going to give advice to me from 5 years ago, I would say this whole front area, this 17-segment display is run by its own Arduino. And there's an Arduino that runs this, which basically just sits there on the serial, and it's a remote frame buffer. So all it does is pump serial data in a slightly compacted format into its own memory and just clocks that out to the screen as quickly as it can. And the advantage to that is that if you've got a piece of channel like along on the front, if you want to remove something to service it or you want to change it to something else, you can just unbolt it, take the USB cable out, throw it onto the table, put something else on. So and ROS helps there greatly, because if you take it off and you go over to your laptop, it's not the robot itself, and you run that Python serial and on your laptop, you can then interact with that screen and debug it on the bench. And when you're happy with that, take it back again.
So you're saying that the more processing units like that you have, the more modular you make the robot, the better it's going to be?
Yeah, for better in cases of easier to maintain, I guess. If you have, I mean, you can get a very powerful micro, but then you're going to have, the trouble with that, the greatness of doing it this way is that you have one micro behind the screen and you run a USB cable to that, and all of the cabling that goes to whatever it's controlling is all local to that. Whereas if you have one very powerful microcontroller, you're going to have a lot of wires going everywhere, and it's going to be quite hairy, as it were.
Thank you, everyone, for your questions. And thank you, Ben, Terry, and your robot minions for your talk today. I have a gift for you, but I feel like I have to pass it to you via Terry, but maybe no more on-stage demo. So thank you, Ben. Round of applause for Ben, everyone.